Now let's discuss Chapter 6. Chapter 6 is a chapter for us to revisit the atomic theory from different perspectives. In this way, we will have a better understanding about the atoms and the structure of atoms, which can be explained for the behavior of electrons, that is in Chapter 7. And with the knowledge of Chapter 7, we can explain the behavior or structure of the molecules, which is pretty much the last chapter of this Chem 1 class in this semester. We'll start off this chapter 6 by discuss the light. Why the light? Because the light, according to the classical physics, is wave. What does wave look like? Wave, according to physics, is a disturbance that propagates, travels through matter or space. A very good example here is you probably have seen that in the gym, some person performing a rope exercise. As you can see that this person holding the end of the rope going upside down, it forms a wave. Because after one circle, the same space, the rope and the end of the rope still going up, it pushes the previous circle at the same point forward so that it can leave the space for the end of the rope going up again. So we start to see the direction of the wave move, which is perpendicular to the movement of the oscillation going upside down. That is what a wave is. And as you probably figured out already, this rope exercise is a way to burn out the fat inside our body, which is costs us energy. With that being said, wave is a form of energy because it carries energy as it travels around. But in chemistry, especially in this class, we are more interested in the oscillation, not the rope, but the charged particle, for example, an electron. When the electron goes upside down, it causes this disturbance in space. And as it goes up and goes down and go up again, the electrical field actually has been pushed going forwards in order to leave the space for another round of disturbance of electric field. In this way, we can see the wave has been generated, but not just by one direction, but also from the other dimension, which is we call the change of magnetic field. So that is why we see the E here is the change of a electro field, and B stands for the magnetic field. And you can see they are alternated going upside down, upside down, and that is how the wave travels. And also you can see the B and goes the same way, magnetic goes the same way. So that is the reason why we call the light not only the wave, we call it as electromagnetic wave. Since the wave carries energy, so we sometimes called light as electromagnetic radiation. According to classical physics, there are three variables for us to characterize the wave. The wavelength, which is the lambda, the frequency with the symbol of nu, and the speed of the wave. In terms of light, so we understand it's going to be the speed of the light. The wave, according to this definition here, is the distance between identical adjacent points on a wave. As you can see in this diagram, if we have the peak of this adjacent electric field, and the distance between these two will be the wavelength of this magnetic radiation. The SI unit for wavelength, because it's a length anyway, is meter. But the more popular unit we're going to see in this chapter is nanometer, which is a 10 to the negative 9th meter. If we talk about some other wave having a shorter wavelength, picometer sometimes can be used. There are some other non-SI unit, for example, angstrom. The A with a small zero on the top. That means 10 to the negative 10th meter. Frequency is the number of circles of the wave undergoes per second. Here, I'd like to call your attention on the unit of the frequency, which is 1/second. And we name this unit after hertz. So don't get confused about the unit of a frequency in hertz. It is the same as in 1/second. So this is something that I want you guys to remember. And when we look at the wavelength, which is meter or nanometer, and when we look at hertz, which is 1/second, so we understand the speed of the wave must have the unit of meters per second. And of course, in the light, everybody knows it's 3.00 times 10 to the 8th meters per second, which is equals to how much? 300,000 kilometers per second. This is the fastest speed we have in this universe. And all of three variables have a mathematical relation, which is the speed of light equals to nu, the frequency, times the wavelength, lambda. And we can also check out by checking out their units as well. Nu is 1/second times the wavelength having a unit of meter. Meter times 1/second, that's meters per second. That is the unit of the speed. So there's also a good advice for us to memorize the formula with the units, because combining the units should give us a certain units that fall in the variable in that category. Since C equal to nu times lambda, and we understand C in this particular case, light, is constant, so we can figure out, or we can solve the nu or lambda by playing math. Frequency would be C over lambda, or lambda equal to C over nu, the frequency. Our eyes are very special because our eyes can interpret the different wavelength of the light into the colors. So that is why we see the various colors in its nature, unlike the other animals like cats or dogs. All they see is gray, black, or white. The numbers here, okay, so like a 750 nanometers, that is what the frequency, so the wavelength is. The number at the bottom, 4.0 times 10 to the 14th 1/second, is what the frequency is. And of course, if we know one, we should be able to figure out the other. So for example, we understand lambda is equal to C over nu from the previous discussion. And C, the speed of light, is a 3.00 times 10 to the 8th meters per second. And according to this spectrum, we realize at this particular wavelength, the frequency is a 4.0 times 10 to the 14th 1/second. And as you can see, we can cancel out the second, 1/second. So we can have the meters. And calculation gives us 750 nanometers. So that proves if we multiply these two numbers together, that should give us the speed of light. Well, when we look at the light with various color, so we call this is a visible region because we can actually see the color with a different, see the light with a different color. But this is just forms a very small and narrow range for a much, much broader spectrum of electromagnetic radiation. So this is what the visible light right here, but you can see this is a much, much broader spectrum of electromagnetic waves. From the shortest wavelengths, remember here is the nanometers. So 10 to the -2 nanometers, that means we're talking about 0.1 picometer. EM radiation with that short wavelength is called gamma rays. Gamma rays is very energetic, and very few doses of gamma rays can cause the permanent damage or even death to the human body. As we move on to the longer wavelengths, we see the X-ray. And we use X-ray for very small dose to check out our health. Okay, so we let the X-ray pass through our body so that we can see something that is not normal, okay, from its image. Next to the X-ray, towards the direction of increase of the wavelength is the ultraviolet. Ultraviolet could be harmful. A little bit of ultraviolet is good for us and to our health because it will make our body to produce more vitamin D, which can help us to absorb more calcium, if I'm not mistaken. But too much of ultraviolet will cause skin cancer. The only one of the two EM radiation that doesn't do us any harm is visible light, as we already discussed. The next to the visible light is an infrared. We actually have the infrared equipment in our kitchen, the stove, because infrared make the molecules vibrate faster. In this way, it can cook up the meat. Next to the infrared, with a longer wavelength, is microwave. And this is what our microwave oven in the kitchen is for. The microwave actually can make the water molecule spin faster. Sometimes it spins so fast, it gets so much of energy, water boils. So that is why we can heat up a food. Remember, our food contains a lot of water. And our food, by heating up water first, then cook up the food. And the rest will be the radio frequency. This is the other frequency. In general, does not do any harm to our health. And here I'd like to point out some frequencies that we use in our communications. For example, we have an AM frequency, the frequency that we use for TV signals. And another frequency that I would like you guys to look at here is the frequency for cell phone. And I want you guys to look at how close this frequency of the cell phone is to the microwave. So that is why some people are concerned about getting the brain tumor when people talk too much over the cell phone with the cell phone right close to the ear. Because the radiation of the cell phone, the frequency of the radiation of cell phone is so close to the microwave, and you know exactly what happens if water meets the microwave. Even though the signal is weak, the intensity is not strong, but over the time, they might cause the problem. So that is the reason why, okay, so we have the invention of a Bluetooth that can lead us to avoid that kind of situation. We, of course, I'm sorry, we carried a little bit too far from our course, but I just want to let you guys to realize, okay, so we have a whole spectrum of electromagnetic radiation. The visible light we observe only constitutes a very small narrow of this much broad of spectrum. From this discussion of spectrum, we finally realize one thing. The nature of a wave we understand is of energy. And from our discussion in the very beginning of this class, okay, and on matter, we realize energy does not have mass. It only occupies space. But when we look at the spectrum, we realize all the various kinds of radiation are perfectly blended with each other without any break. That means this radiation is continuum in energy. So we cannot cut them. And they are continuum in energy, they are continuum in frequency, so on and so forth. It's not like the particles. We understand particles are matter because not only they occupy space, they also possess mass. By having mass, particles are individual. That means they have a fixed quantity and they are discrete from each other. That is what we call the particle wave, the difference between the two. So classical physics makes very clear about a wave is not matter. And not the matter, not wave or energy. This distinction between matter and a wave met his first challenge over the problem we called as a photoelectric effect. When some piece of metal shines by the UV light, for example, we'll see electrons coming out. Later on, it is proved they are electrons. And those physicists are asked to explain how it happened. The first impression they got was the radiation bombards the particle out. Well, does it make sense in physics? Let's think about boxing. So when two boxers fighting on each other, if the punch is so hard on someone's face, you may probably see the teeth knocked out. It's kind of like knocking out an electron from an atom. There must be the collision of two particles, because throughout this collision, the energy can be transferred. So the energy pulse will knock out the teeth or knock out the electrons out. Remember, as we said before, EM radiation is energy. It is not a particle. That means we can feel the energy, but we can never feel the punch from the sunshine. How come this field of the sunshine can knock out electrons? So that is our first failure of classical physics explaining this effect. The second failure is the threshold frequency. According to classical physics, frequency has nothing to do with the energy of the radiation. Come to think of it, we have the same sun, the only sun, and we're going to feel the heat differently from Florida if we are in, say, Alaska. It is the intensity of the light that makes the difference, hot or cold, or the intensity of the energy. It has nothing to do with the frequency. Then how come frequency becomes quite an important role in knocking electrons out in this effect? No solution whatsoever. And the third one will be the kinetic energy of the electrons. Since the second one cannot be explained, the third one neither. Speaking of a threshold frequency, that means the frequency where the electrons start emitting. So for the UV light, it has to reach a certain frequency in order to have electron emit. Once it reaches the frequency, no matter how dim the light is, you start to see electron coming out. Much fewer, but there will be electron coming out. If the frequency does not reaches that so-called threshold frequency, no matter how bright the light is, no electrons coming out. So this is a complete failure in classical physics in an attempt to explain this so-called photoelectric effect. It was Albert Einstein in the year of 1905 explained this effect in one of his articles of 6. Later on, people find out that those 6 articles were so shocking in physics because that 6 articles actually covers the 3 very different fields in physics. So that is why I make Albert Einstein a household name and one of the giants in physics. In one of the articles published in 1905, he said we should think about this electromagnetic wave as particle instead. Because according to physics, only particle can knock electron out upon collision. That is the law. It cannot be changed. The one thing that we can think about is to propose the particle, this radiation as particles. And later on, he even gave the energy of this particle of the light. He said the energy is equal to h times its frequency. H is later on named as a Planck constant. It has the value of 6.626 times 10 to the negative 34 joules times second. This is a very famous constant, a very important constant in physics. Pretty much like the universal gas constant in classical physics. Okay, so now that we know this particle has the particular energy which is directly proportional to the frequency, remember frequency is equal to speed of light divided by the wavelength. So we can replace the nu with the c over lambda. Now we have a much better picture to realize that the higher the frequency, meaning we are going to have a much shorter the wavelength. The energy as a result gets greater. With a simple equation in E equal to h nu, now we understand the kinetic energy of the electrons emitting from the metal actually is the h times nu minus threshold frequency. Because if you have extra, say extra frequency after subtraction, and that frequency will convert into the energy, kinetic energy of the particles to move. So this is a very simple assumption of particles of light. E equals to h nu explains the three problems that classical physics cannot explain. And in 10 years, 1915, it was proved by the R.M. Millikan. That is why Einstein got his Nobel Prize in 1924, not because of a theory of relativity, but because of this, for the electric effect. And because E equal to h nu is one of the equations that's widely used in quantum physics, so Einstein is considered as one of the founders of quantum physics. Well, what do we learn from this Einstein's model of treating the light as particles? We definitely realize that it's going to be wave-particle duality of this radiation. So how can we understand this duality? Because according to classical physics, wave is wave, particle is a particle. They are not related. They are totally different. So how can we imagine this? One example probably will help us to understand this. So imagine that we have a coin. The classical physics just focus on one side of a coin so long, so much, and it does not realize there's another side of a coin, okay, another face of the coin. So once we tilted a little bit of this coin, we realize, hey, this coin has two sides. So that's what the duality is for. And of course, this particle of light is called photon. The smallest possible amount of EM energy as a particle. And one thing I'd like to emphasize, especially for the mathematical part of this chapter, is E equal to h nu. Although as simple as it sounds, it is for the energy of one photon and one photon only. Okay, so keep in mind with this conclusion. And with this photon concept, now we can treat the photon as particles so that photon can be discrete, and most of all, it has the fixed energy because different frequency results the different energy of the photons. In this section, the section 3 of the Chem 1 class, there's only one type of calculation problem, which is related to the photon. So now let's look at this math problem about a photon. We got a laser that produces a red light of a wavelength of 332.8 nanometer. So we are asked to calculate the energy. I want you guys to pay attention to the unit right here. In kilojoules of 1 mole of photons in this red light. Okay. As we try to apply our knowledge to the unit analysis, we realize there's only one piece of complete information, which is 632.8 nanometer. And we realize that is the wavelength. How do I know it's wavelength? It has a meter as its unit. Right? It's a length. And we talk about a photon here. So that's the wavelength. All right, so once we have a wavelength, so what is the question wants? Question wants a kilojoules of 1 mole of photons. We have done so much about splitting units into a conversion factor or in the format of a conversion factor. Now it's time for us to put it back. Kilojoules of 1 mole of photon equals kilojoules per mole of photon, which is kilojoules slash mole of photons. So here is photons. What is the mathematical approach we should use to solve this kind of a problem? Because the keyword is a photon, so we realize E equals to h nu. Do we know what the nu is? No. So we need a second equation. C equals to nu times lambda. All right, so once we have all this in mind, so we can go ahead and solve the problem. We replace nu with C over lambda, and both C and h are the constants. Lambda is known, so 632.8 nanometers, we put them at the bottom. And we realize that we can cancel the second because second times 1 over second, so they can cancel. But we realize we cannot continue the calculation because we got meters and nanometers. We have to find a conversion to convert the meter to the nanometers or vice versa. So we have the conversion that convert nanometers into the meter. Remember, 1 nanometer equals to 10 to the negative 9th meter. Because we want to cancel nanometer, so we put the 10 to the negative 9th at the bottom that goes along with the meter. This calculation gives us 632.8 times 10 to the negative 9th meter. Of course, you can write it this at 6.328 times 10 to the negative 7th meter. It doesn't make much difference there. And this way, so we find out we can cancel meters, so that leaves us the joules. Joule is a unit, right? Because we notice there's a kilojoule, so joule should be the unit for its calculation, because joule is a unit of energy anyway. So let's carry out the calculation. We found 3.14 times 10 to the negative 9th joule. Is that it? No, it's not. Why not? Because question asks for kilojoules per mole of a photon. But all we have is joule. It's not enough. We need to do a little bit more. What more should we do? I would like to jog your memory a little bit. E equals to h nu is for, you're right, single photon. That means for this particular photon, it has such energy for 1 photon. So we did adapt the units from joules to joules per photon. All right, so once we realize the new unit, joules per photon, in order to get a kilojoules per mole of photon, things becomes much, much easier. First, we convert joules into the kilojoules. Second, we realize that the mole should be at the bottom as a unit. So let's set it up by putting mole at the bottom. What do you think the number should be on the top? You got it? I forgot your number. Because 1 mole, according to its definition, 6.022 times 10 to the 23rd. Carry out the calculation by multiplying everything on the top divided by everything on the bottom. We got 189 kilojoules per mole of photon. When we look at the energy of each individual photon, is not much, 10 to the negative 19th joule. But when we put 1 mole of photons all together, it's going to be quite a amount of energy, 189 kilojoules for this 1 mole of photons. Why do I have to make a bigger fuss about this? Because this is the energy that photosynthesis uses to initiate in producing glucose and oxygen. There's a famous experiment done by Isaac Newton. So once we have a light passing through the dark room, and if we put the triangular prism in the pathway of the light, the sunlight, and we got yourself the rainbow. And we find out there's no breaks among all these 7 colors. So we call this continuous spectrum. All the different colors blended into one another without any breaks. And according to physics, that is the result of a hot black body. And what's a black body? That is a little bit of overall scope of general chemistry. And if you have to take physics, I believe your physics professor will discuss this. That's very interesting stuff, because this is where we got a Planck constant. Well, how about if we put this prism in a pathway of the light emitted by the hydrogen lamp? Because when we light up a hydrogen lamp, the lamp is filled with hydrogen gas. If we fill this lamp up, and fire this lamp up, and it gives us some kind of a white color, a little bit of purplish, but it's purplish white color. But as we put this prism in, we realize it is not a continuum spectrum. It is, as a matter of fact, the line spectrum, because all we see is the 4 lines with different color that's in the black background. As you can see, we got 4 lines: red, green, blue, and violet. Some people probably only see that it's 3 lines, depending on the eyesight. And this kind of spectrum is called emission spectrum, because we see the lines from the black background. If we put a scope and aiming that to the sun, among all the lines, dim lines we see, we can see that 4 lines as well. So when we see the dim lines from the continuous spectrum, we call this absorption spectrum. Regardless of what spectrum we are talking about, there are always going to be these 4 lines at very specific position with a very specific frequency. So special, so specific, we can actually use these 4 lines to identify hydrogen gas. So those line spectrum becomes the fingerprint of the element for us to identify. So here I'd like to take the chance to tell you a story about the discovery of our second element in the periodic table. If you happen to have the periodic table of elements nearby, you probably will notice the name of this second element. This second element was discovered not on Earth, but from Sun. Because once people realize the long spectrum, the first choice they want to check out is Sun. So once they took off those 4 lines from the spectrum, which is hydrogen, they realize that there's another set of lines that should belong to something else. And somebody was boldly enough to publish the result and claimed that there is a new element in Sun. Okay, he convinced the entire society. So whoever find an element got the privilege to name such element. So that person started to think about the name of the element. So this is how he came up with the name of this new element. This element was discovered from Sun. Okay. And according to the ancient Greek, the name of the sun god is Helios. Yes. And as he looked at the periodic table that he got at that time, most of the elements, because they were metals, ending with IUM. In order to play safe, because there are so many metals in our periodic table, so he picked IUM as its suffix to make the name of such element. Do you know which element I'm talking about? Helium. Yes, helium. Number 2 element in our periodic table. So that is the reason why you realize for the rest of the element in that group, neon, argon, krypton, xenon, radon, they all end with the suffix of On. Why helium is so special? Because this is the element that was discovered not on Earth, but from Sun. 50 years later, when somebody dig a hole on the ground somewhere in Oklahoma, a gas coming out. When people collected those gas and sent into the library or the laboratory, they find out that this is a gas of helium. And it is a gas belonging to the group 8. However, it's too late to change the name. So the name, change the name of helium to helium. And by the way, okay, this doesn't sound good either. So the name of helium stuck. So that's the story of discovering elements. So that's why we got helium on the top with the rest of the element ending with On. So if you're interested, okay, there is a book called The Story of Discovering Elements. I don't know exactly the name of this, but if you can have a chance to take a look at it, there will be a lot of fun stories about how people name the elements. We need to go back to this chapter 6. Line spectrum is something that the classical physics don't even dare to explain. Because frequency, again, has nothing to do with the radiation, according to classical physics. So, in the year of around 1910, there was a young scientist, Niels Bohr, started to think about how he could answer that the line spectrum from the hydrogen. The reason why he chose hydrogen because hydrogen is the simplest atom. One proton, one electron, that's it. And being a physicist, he knew that for sure. If we deal with a two-body system, we can have precise and exact solution mathematically. So that's why he started with the hydrogen. And there's a lot of paper published about the spectrum from hydrogen lamp. So he got enough the background, and he started to think about if there's a way for him to explain the whole thing. One day, as he passed through a picture, which is the one you're seeing right here, the solar system, something struck his mind. So he just thinks, why can't we think about an atom as a mini solar system? You know what I'm saying? The nucleus, which is only proton, right? So the proton should be considered as sun. Electron like a planet. And what's even more interesting to him is there's nothing between the major planets. Every major planet will follow its own orbit. Can the electron has its own orbit circling the sun, like one of the planets circling the sun? Or is there a set of orbits, like the orbits those planets have in the solar system? So with that kind of a thought, he proposed in his model of hydrogen. He said, electron and hydrogen circling nucleus only in the specific set of orbits. Orbits has been mathematically simplified as the circle, concentric circle. So that means the center point is right on the nucleus. And all the circles must have the fixed radii. And he tried to relate those circles with one radii. He said, okay, the first orbit must have the radius that is 1 times the smallest radius that the atom can allow. Because if electron goes any closer, it might just collide on the nucleus. So that is why there is a minimum distance that is required for electron staying away from nucleus to become stable, or to become stability of the atom. Okay, so that is our first orbit. For second orbit, the radius of this orbit must be twice of the smallest the radius. So in this way, so he can use a multiple to describe those orbits in a set. So he said for the third orbit, it must be 3 times of the radius. For the fourth circle or orbit, it must be 4 times of the radius, on and on and on. And now we have a multiple in a certain value. And later on we'll realize, as you probably already realized, that is the quantum numbers. And further on, he said each orbit must be associated with a definite energy level. That certainly makes sense, just like those orbits, just like those planets. They must have the different energy, right, when they're surrounding the sun. So that certainly makes sense. So there's no doubt. And as is shown in this picture, the first orbit must have the lowest energy according to physics, because as the electron moves to the second orbit, actually there's kind of like a spring has sprung, storing more energy. In this way, the closer the electron to the nucleus, the more stable the electron becomes. According to this, people can draw the conclusion that the first orbit is the lowest, and we call it ground state. For the rest of the orbits, we understand they are excited states because the electron is not going to be stable when they fall in those orbits in terms of energy. There's a myth there that electron does not radiate energy while in any one of these orbits. Why? Myth. Cannot be explained. And in order to make such postulation, he tried to prevent people arguing about electron radiates energy while it going circling around the nucleus. Because if you can draw the circles, and if you turn it at 90 degrees, you'll find out one way to think about this circling of electrons is just like oscillating, going upside down. And we understand if we have an electron, a charged particle going upside down, it emits EM radiation. Remember, EM radiation is a form of energy. By doing oscillation or circling, electron loses energy. When electron loses energy, it gets closer to the nucleus, and eventually it will collide on the nucleus. So that is why the main reason classical physics failed to explain the hydrogen atom. When an electron moves from one orbit to another, there's an exchange of energy. From lower energy to higher, from say n equals to 1 to second orbit, atom absorbs energy from various kind of energy. It could be heat, it could be electricity, so on and so forth. But once we have electron from a second orbit falling back to the first, it emits photon. And we understand that delta E equal to the energy difference between the two states, and equals to the energy of photon, and equals to h nu. This is where Bohr's model borrows the idea from Einstein, E equals to h nu. With all of these assumptions, or the postulation as we call it, he carried out the calculation. The calculation itself is quite complicated, but in the eyes of a physicist back then, it was simple. The result was astonishing because the energy of the electron, or whatever the orbit, actually has nothing to do with the size of the atom. How do we realize? Because there's no radius as the variable of this equation. The energy of the atom is the only function of the multiples, n, the square of n actually. So that makes this a set of multiples 1, 2, 3. Remember, that is just tells us how big the circles in terms of a radius, right? So those orbits. So that makes this set of numbers on the multiples a lot more important than people thought it was. Since they are so important, that number is so important, so we call them as a principal quantum number. And I'm sorry, there's a mistake. We need to cross out that 0 because it can never be 0. So now that those multiples have the name called principal quantum number. And from that equation, it's obviously to have people realize that we have those orbits. We can label those orbits by those principal quantum numbers. For example, first shell, third shell, on and on. Why we prefer to call it shell? Because remember, electron moves in 3 dimensions. So once in 3 dimensions, it's kind of like an eggshell in space, with the various sizes, of course. And of course, as shown in this picture, the less the value of n, the smaller the orbit. The smaller the orbit, the closer the electron to the nucleus. The closer the electron to the nucleus, the lower the energy state of the electron is at. And of course, there's a lot of other names called energy shell or energy level, but they all mean the same thing, energy state. And once the electron changes the orbit or changes shell or the level, that comes with the energy exchange. If the electron jumps from the first shell to any other shell, it is going to be an excitation. Because remember, other shell has more energy than the first shell. So first shell is what we call the ground state. The rest shells are called excited state. And when electron try to jump back from outer shell to the inner shell, that is what we call it relaxation. That is going to emit photon according to the assumption or the postulation of the Bohr's model. And according to these conclusions that he drew from his model, Bohr explained those 4 colorful lines in a spectrum. So the red line actually is the relaxation of the electron from the 3rd orbit to the 2nd. Green, 4th to the 2nd. Blue, 5th to the 2nd. And the violet, that would be 6th to the 2nd. What about the 7 to the 2nd, 8 to the 2nd? That will go to the ultraviolet region, which we cannot see that in our bare eyes. And the values he provided, the calculation he provided, makes perfect match with those wavelengths that the people experienced or people observed. But there's more. What about electron goes all the way back to the 1st orbit? That would be called as a Lyman source, Lyman series, as you can see right here. I cannot find it. As you can see right over here. This is where we start to see all the electrons from various states falling back to the first orbit. And since they cause too much of energy and emit, so it's in the ultraviolet region. And later on, Lyman discovered those set of the lines. What about on the third? Of course, that would be called as Paschen series that occurs in infrared. So not only it explains those 4 lines in the visible region, and he extended and explained it to the other series. That shocks the world. That is why within 10 years he got his Nobel Prize in physics. He got Nobel Prize even earlier than Albert Einstein did. I believe it's 1921, if I'm correct. However, it became outdated in the next 10 years. So you may ask why we still explain this, since it's already outdated, right? So the modern theory has expanded that Bohr's model. So why do we have to talk all about it? Because this is the very first model that introduced the concept of quantum numbers. And the calculation is much easier compared to the ones that we're going to discuss in mathematics. With that calculation, everybody that graduated with a physics degree can follow. So that is why it was so popular back then. And it's worthwhile for us to introduce this model, because from this model, we now learn how important it is for quantum numbers. Now, let's talk about quantum chemistry. We can approach the atomic theory with the quantum chemistry, or quantum physics, actually, because we talk about the same type of atom, so they should be called quantum physics. Throughout the series of mathematical work, we now come to understand that in order to locate an electron, or the space where we can find electrons the most, so such a space is what we call atomic orbital. We need 3 quantum numbers, kind of like coordinates. In order to find or locate an object in 3-dimensional space, we need x, y, z 3 coordinates. But the relationship between the 3 quantum numbers is much more complicated than just a simple x, y, and z. So how are we going to be able to understand this atomic orbital? Atomic orbital can be thought as a room for electron to stay, like in an office for Dr. Lee to have during the office hour. All right, and we're going to use that office for Dr. Lee as an example to explain that 3 quantum numbers, or the relationship of 3 quantum numbers later on. But let's go through these 3 quantum numbers first. The first quantum number, again, we copied the name from Bohr's model. we still call it principal quantum number. For the principal quantum number, it starts from 1, then 2, 3, all the way to infinity, if we want it. So the principal quantum number could be any positive whole value, whole number. 0 can never be the principal quantum number. The functions of the principal quantum number is as such. First, it determines the size of the orbital. Remember, if we use the idea of orbit, so we realize just how great the orbit that we can find the electron. Here, instead of orbit, we just use orbit, just how big this orbital in a space where we can find the electron. So n still is a refraction of the distance of electron from the nucleus. Second, it determines the principal shell in energy. If we have atomic orbital with the same n, that means they must be in the same shell. We bought a shell from the Bohr's model as well to tell, okay, so that is the energy level that an electron must have. Why we so focus on energy level? Because this is the only thing that we can actually measure about the electron. And of course, the higher the n, the further away the electron from the nucleus, such orbital or the shell must have the greater energy level as well. The second quantum number is called angular momentum quantum number. We use L to represent such number. And the L can have a 0 to begin with, then 1, then 2, and there's a limit. The limit is n minus 1. In other words, L, there's a second quantum number, angular momentum quantum number, is determined by n. And that is always true for L less than n. While the L can start at 0 and it changes its value by 1 at a time and ends with n minus 1. So for example, if n is equal to 1, what the value of L do we expect? Of course, it starts at 0. Do we have another value of L, say 1? Of course not. Why? Because L can never have the same value as n. Why? L is less than n, period. That makes only one possible value for L if n equals to 1. The value of L is 0, and 0 only. And of course, if you want to do n equals to 2, we find out that L can be 0, then 1, as long as the value is less than n, but it cannot be 2 for L, because now it's against the rule for L equals to 2. As functions of this angular momentum quantum number, there are going to be quite many. First, it determines the shape of the orbitals. Orbitals comes from the various shape, as we will discuss at the end of this chapter. And also determines the number of the shells in energy. Various value of L indicates the different energy level of these subshells. And each value of L represents a subshell. L equals to 0, L equals to 1. They are two very different subshells. Why do we call it subshell? Because they all come from the same principal shell. Another thing that I'd like to point out here is the total number of possible values of L equals to the total number of subshells, which is equal to the value of N itself. People usually put those principal quantum number and this angular momentum quantum number all together because combination of the two make the energy level definite. But when we put these two numbers together, then we're going to have a problem. So for example, N equals to 1, L equals to 0. If we put these two numbers together, people might misunderstand the number as 10 because it's 1, 0. Therefore, people start to use letters to represent the values of L. For example, S for L equals to 0, P for L equals to 1, D for 2, and F for 3, G for 4. In chemistry, the first four quantum numbers L is sufficient. 0, 1, 2, 3. In letters, S, P, D, and F. And of course, I want you guys to memorize, I want you guys to memorize this table as long as we are in this section. The third quantum number is called the magnetic quantum number, m sub L, because this quantum number is determined by L. Since L is determined by N, so ultimately m sub L is also determined by N. So what is the rule for m sub L in terms of values? Kind of like L, start with a 0, then it goes with a pair. Plus minus 1, plus minus 2. That means plus 1, minus 1, plus 2, minus 2, until it hits the L itself as plus L and minus L. The function of m sub L identifies the individual atomic orbital by its spatial orientation. That means from the specific orientation in space can we find this individual atomic orbital. And each value of m sub L identifies an orbital. In most of cases, we don't care which m sub L for what atomic orbital, but we do care about just how many orbitals that m sub L represents. I just want you guys to understand each value of m sub L indicates or identifies an atomic orbital. So now let's look at the relationship between m sub L and an L. And as we understand here, if L equals to 0, the letter we use is S, because S means L equals to 0. And according to the rule here, for us to pick up the value of m sub L, we only got one choice, 0. Because we cannot go plus minus 1, because L equals to 0. So we have only one choice. And there's only one value of m sub L, suggests there's only one orbital, because remember, each value of m sub L identifies an orbital. Alright, so now we understand for m sub L, they always start at a 0. And if we have L at that equals to 1, the letter we pick is P. Now we got 3 different values of M sub L because we have 0. Since L equals to 1, so plus 1 and minus 1 are also allowed. 3 different values of M sub L, meaning 3 different orbitals. If L equals to 2, the letter we use here is D, and 5 different values of M sub L, 0, plus 1, minus 1, plus 2, minus 2, so 5 orbitals. So now we make perfect sense about the M sub L. So we say M sub L always start at 0, then going up as a pair. Plus 1, minus 1, plus 2, minus 2, until it hits plus L and minus L. And when we have L equals to 3, so we realize that there's going to be 7 orbitals because there are going to be 7 atoms, so the different values of M sub L's. And when we look at those number of orbitals with the L, we suddenly realize the mathematical relation is 2L plus 1. 2 times 1 plus 1, that's 3. 2 times 2 plus 1, that's 5. 2 times 3 plus 1, that's 7. So the total number of possible values of M sub L, which just equals to the number of orbitals, that equals to L plus 1. And we all know there's a limit for us to pick M sub L because it's up to plus minus M. And this rule is very important for us to pick the various values of M sub L because we cannot go any further. We cannot go beyond plus minus L for the values of M sub L. We can always start with a 0 and go in with a pair. All right, so now that we learned our 3 quantum numbers, let's talk about the energy level, because this is all the observation we can make when we try to investigate the electrons in the atom. The energy levels for the electrons in the atom can have 2 folds. First, it's the principal shell, what we call the shell or level, that is determined by N. And we understand that less the N, the greater the probability where electrons can be found, that is also closer to the nucleus, the lower its energy state. And we also have a subshell, or what we call sublevel, which is determined by the L. Kind of like if you want to get to the EFSC, first we have to get ourselves into the Brevard County. So the Brevard County kind of like N. And the EFSC has 4 locations that is determined by the L. Okay. It may not exactly fit with this analog, but I just want you guys to understand. Okay, only N and L together, like EFSC Melbourne campus or EFFC Palm Bay campus, that make the energy definite. Okay, so only combination with N and L make the energy state of the electron definite. Kind of like if we have EF, so EFFC Melbourne campus make our location definite. Orbitals having the same values of N and L are said to be in the same subshell. And we'll try to explain all of this, explain this statement with a different analog in the next slides. The total number of orbitals in a subshell is equal to 2L plus 1, and we call that as degeneration in energy because they all have the same energy level. Why 2L plus 1? Because when L equals to 0, we understand we are talking about an S subshell. There's only one orbital in it. As we try to exhaust the possible value of M sub L with this various L, as we just demonstrated in the previous slide. And when L equals to 1, we talk about a P subshell. There are going to be 3 orbitals. All 3 orbitals have the same energy. And D subshell will have 5 orbitals. And F subshell 2 times 3 plus 1, so that's 7 orbitals. You may have heard about Px, Py, and Pz. So these are the 3 atomic orbitals for P subshell. Y, X, Y, and Z, because those subscripts of Y, X, Y, Z are the orientation or spatial orientation where we can locate those orbits. So for P orbital, so we can find one orbital sitting in the x-axis or sitting on the x-axis, and we have a Py, the another orbital sitting on the y-axis, the third on the z-axis. So that is why we use x, y, z. And for D subshell, those are 5D orbitals. You have x, z, y, z, x, y. That means those D subshells can be found in the plane formed by x and z axis, y, z axis, and x, y axis. The other two is going to be something quite special, and we're going to talk about it. Excuse me. We're going to talk about it, okay, as we talk about the shape of the orbitals. All right, now let's take a look at it, the hierarchy relationship among all 3 quantum numbers. Remember, L is determined by N. M sub L is determined by L, which is also ultimately determined by N. So just what kind of hierarchy relationship we have among all 3 quantum numbers? Let's pick up the first 4 principal quantum numbers. Remember, N cannot be 0. They only start at 1, so we have a 1, 2, 3, and 4. If N is equal to 1, according to the rules here for the L value, it's 0. Right? Can it be 1? If it is equal to 1, then L would be the same value as N itself, which cannot be allowed. Remember, it has to be N minus 1. So L is always less than N. So 1 is not allowed. The letter that we use to designate L equals to 0 is S. So that's why this particular shell is called 1S. If L equals to 0, we understand M sub L is equal to 0. Do we have a plus minus 1? No, we don't. Because if L equals to 0, the limit is plus minus 0, which is 0 itself. So we only got 1 possible value of M sub L. Since there's only 1 value, there's 1 orbital. 2 times 0 plus 1 gives us 1 in mathematics. That is pretty much it for the entire principal shell, the first shell. So the total number of orbitals in the shell is equal to 1. So here I'd like to use 1 square to represent this 1, because 1 square equals to 1. That's it for the orbitals in the first shell. What about the second shell? For second shell, we understand for the value of L, we can always start with a 0. Then 1 now is allowed, because 1 is less than 2. What about 2 for the value of L? No, it's not, because we cannot have a value of L that is equal to N. And of course, as we go on for the L equals to 0, so that's going to be 2S, and m sub l equals to 0, and there's going to be one orbital. And then people are probably going to get confused. How come we have the same value of L, same value of m sub L for n equals to 2, like it used to have for n equals to 1? In order to answer this, or to clarify this, I would like to use myself, okay, to illustrate this situation. So say somebody is going to meet Dr. Lee in his office during the office hours. And you probably know my office is in Building 5, room 138A. So here I'm going to separate those numbers as 3 major quantum numbers. Consider myself, Dr. Lee, as an electron. Okay, so my room, okay, as an atomic orbital, okay, as we think about my office, is Building 5, 138A. And I can think of that number in 3 different groups. First, building number. I can take a building number as the principal quantum number of electron. Because on our campus, we have as many as 16 buildings now. My building is number 5. So quantum number from building 1, building 2, on and on and on, all the way to building 16. Right? So for electrons, they can have the principal quantum number from 1, 2. Only this time, they can go as far as they want, the electron wants, to infinity if situation allows. Well, what about a second quantum number? Like the L in electron. The second quantum number I'd like to take is the floor in the building. 138A. So the 1 here indicates that I'm in the first floor. I'd like to remind you, each building has a first floor. So just like, regardless of what n value is, as long as there's an n, there's always L equals to 0. We can have a building with only 1 floor, first floor, in terms of L equals to 0. And we can second floor, third floor, fourth floor, on and on and on. Right? So that L actually is like a floor, so there are always going to be the same floor, the first floor, in every building on this campus. So there's going to be L equals to 0 in every value of L. L equals to 0, there's going to be, okay, for n equals 1, L equals to 0, for n equals to 2, L equals to 0, for n equals to 3. I just hope that explains why we can see the same S in the different shells. What about m sub L? M sub L is just like the room number on the floor in that building. So for m sub L, always going to be 0 for electron. Just like there are always going to be 101 room in every building. Right? Number 01 room in the first floor in any building. So I just hope by using my office to help you to understand those relationships between N and L, L and M sub L. Well, let's continue our discussion about this hierarchy relation among the quantum numbers. Now we have L equals to 1 for second subshell, for second principal shell, And the letter for 1 is P, as we already know. And there are going to be 3 possible values of m sub L because we have plus 1, minus 1. Total number of orbitals is going to be 3 as 2 times 1, the value of L plus 1. That's it for all the orbitals in the second shell because we only have 2 subshells. So 3 plus 4, or 3 plus 1 equals to 4, and that is 2 squared. So from 1 squared to 2 squared, we suddenly realize that the total number of orbitals in the shell can be considered as n squared. Let's check it out whether that is correct or not. Okay, for n equals to 3. For n equals to 3, L can be 0, 1, and 2. Will that be 3? No. Again, because L cannot be the n itself. Again, for L equal to 0, we talk about 3s. For L equals to 1, we talk about 3p. And we have 1 orbital for 3s, 3 orbitals for 3p, and we got a new one, L equals to 2, and we call it 3d because d is for L equals to 2. How many m sub L's? We got 5 m sub L's, meaning 5 orbitals, make it a total 9 orbitals, which is 3 squared. As a matter of fact, we can actually prove this from mathematics, right? So if we add all the odd numbers together, okay, the sum would be the number of the odd numbers we add together squared. Now, let's look at n equals to 4. So as we can see, we got the 4 different values of L. And we got a 4s, 4p, 4d. The only thing new here is for f, because f is for L equals to 3. And we have a 7 possible values of m sub L, indicating we have 7 orbitals. When we add them all together, 9 plus 7, it's 16. So 4 squared. So from this slide, I just want you guys to understand those relationships among those 3 quantum numbers. I hope the analog of the office number explains or help you to understand those relationships. All right, now let's try to check out some of the example problems. Now that we have equipped ourselves with those 3 quantum numbers. Okay, the first type of the numbers regarding the quantum numbers, so the examples regarding the quantum numbers are as such. So question wants us to figure out what is wrong for each row of quantum numbers and the name. Before we can answer that, I always want you guys to remember the rules in picking quantum numbers and the letters that are used to describe the various value of the angular momentum quantum number. So n must be greater than 0. Always start at 1, 2, 3 as long as it needs. L has the value that is always less than n, can always start with a 0 and keep on going until the value that it's cannot go any further. M sub L is up to plus minus L, and we can start from 0 and keep on going until it hits plus and minus L. There's the various letters that are assigned for the value of L. I usually memorize as such 1, 2, 3, 0, 1, 2, 3, S, P, D, F. Okay, now I'm going to put these rules aside. So let's see what's wrong with those combinations of the quantum numbers and the name. If n equals to 1, we understand L cannot be 1 because L can never be the same value as L. So that makes L value 0, because this is the only value that is allowed. Alright, so for L equals to 0, A would be S. So that is 1S. What is wrong with the second row? If N equals to 4, L, it could be any value, positive value that's including 0, that's less than 4. So 3 less than 4, L is good. What about the M sub L? As long as it's a value within the range of -3 to +3, it's good. So this value is good. That means something wrong with the 4D. If you check out the table right here, for L equals to 3, we realize it's F. So the name is wrong. We should have called it 4F. The last row, N equals to 3, L equals to 1. That's good, right? Because as long as we have L that's less than N, that's good. But we see something wrong with -2 for M sub L, because M sub L can never go beyond -1 to +1. So with L equals to 1, M sub L can have only one of these three values, 0, +1, -1. Second type of the exercise regarding these quantum numbers is fill in the blanks. Again, and I'm going to put these rules on the side that will help us to fill out those blanks. Alright, so if we have a name of 4P, we understand 4P indicates the right N equals to 4. What the P indicates here, that's 1, right? So L equals to 1. That's it. What is the name you have if we have these three quantum numbers all together? N equals to 3, N is good. L equals to 2, which is good because as long as L less than N, we are good. M sub L, what do you think of a -2? Is that good? Yes, because M sub L can be any value that starts from -2 all the way up to +2. So let's say up to plus minus L. So from -2 all the way up to +2 could be any whole number within that range. Okay. For the name, for the subshell, so that's going to be 3, right? L equals to 2, that would be D. So we call it 3D. What about the last one? 2S. We understand N is equal to 2. S is L equal to 0. And with L 0, M sub L has no any other choice but 0. This question is one of the most popular type question that we probably will see in our exercise as well as in our exam. So question just simply asks which combination is not allowed. Again, I'm going to put these rules on the side. So let's see those one by one. All right, question wants to see which one is not allowed, right? So what about first choice? 2, that's good. L equals to 0, less than 2, so that is good. M sub L, 0, so that's good. All right, N equals to 4, good, as long as it's positive value, whole number. For N, that's good. L less than 4, that's good. M sub L, a number that's within -3 to +3, so that's good. The third choice, n equals to 3, that's good. L equals to 1 less than 3, that's good. M sub L, 0, and 0 is one of the M sub L that is allowed, okay, if L equals to 1, because it could be 0 plus 1 minus 1, 3, so it's 1 over 3, so that's good. And when n equals to 5, that's good in choice 4. L less than 5, that's good. M sub L, however, we see the problem, because M sub L cannot go beyond plus minus L. So that's why our choice 4 is the answer, because it's not allowed. And also, just for the sake of more practice, we can see choice 5 to see whether that is correct. N is 7, good. 1 for L less than 7, that's good. Plus 1, that is also good, because plus 1 is allowed for M sub L if L equals to 1. Okay, now let's look at the last question in that example problem. So now, question wants to know what is the set of quantum number that is correct for an electron in the 3D orbital. 3D orbital, according to the rules we put there on the side, 3 means n, right? So we understand 3 is n. D, according to the table here, means L equals to 2. All right, so that means when we look at those choices, all we need to look at is n equals to 3, L equals to 2. So that kicks away number 1, 2, and 4. But they're not good. And between 3 and 4, we find out M sub L has the value greater than L itself, so that is wrong. So that makes so choice number 5 a correct answer. Well, let's talk about the shape of the orbitals. Remember, it is the L determines the shape of orbitals. So when L equals to 0, we have only one orbital because we have only one value of M sub L. The shape for that is a sphere. So as shown right here. So that is the whole graph, whole sphere look like. This is just a quarter of sphere look like. And the greater the n, the bigger the size of this sphere, right? Because as we look at the 2s, so it gets bigger. For 3s, it's much, much bigger. But what is interesting for us to understand here is what happens to this white stuff, white circle. The white circle actually is called spherical node because this is the region where we cannot find electron, period. So no probability in finding electrons. Kind of like Dr. Lee can never say, I'm not going to say it, jump to the second floor in his office, right? Because there's a ceiling. So there is a 0 possibility to find Dr. Lee stuck in on or off. Rather than we put say on the ceiling. That's a 0 possibility. So kind of like the same situation for electron. So there's the place where no possibility in finding electrons, just like ceiling is the place there's no probability in finding Dr. Lee hanging on it. Number of a spherical node actually is equal to n minus 1. That means if we have one s, that will be no spherical node. And if there's 2s, that will be one node in white. For 3s, there will be two nodes. The node says no probability in finding electron. Does not necessarily means, I like to emphasize again, does not necessarily means that electron cannot be found anywhere else. That means electron can be found in 2s, for example, in somewhere that's in a space of 1s. So let me put in the blue. So this is where we can find some probability of 2s electron. That is what we call the tunneling effect or penetration effect. And that is quite important because electrons, just like a Houdini or some mathematician, that can actually penetrate the wall. I believe there is an American magician shows the magic in China to penetrate the Great Wall of China. So I know that is just like some kind of scene, but that is true for electron. Electron can actually penetrate some certain energy barrier to go the other places. Like this penetration or tunneling effect. And of course, if you have 3s, as you can see, that not only we can find the electrons here, we also can find some 3s electrons right here, and finally in 1s. Although the probability gets smaller and smaller once it gets closer and closer, but it is always possible. That is for the s orbital. And I would like to remind you, s orbital sphere, that means in one piece, right? So that's we call it in one lobe. For p orbital, where L equals to 1, now we find out the shape actually is a dumbbell. Okay, that is one ugly dumbbell, but that is looking pretty good for a dumbbell. And you may wonder what's the difference? The difference is we take the square of this shape and it becomes like this. And dumbbell has two lobes. It has to be turned out that the number of lobes equal to the 2 raised by the power of L. If L equals to 1, 2 power of 1 is equal to 2. So this is the lobe that the electron is going to spend time with. So electron could have two places to go to. And as for orientation, those dumbbells lies along the axis. Why two lobes? Because there's a nodal plane, as we shown right here, as you can see right here, right? So this is a nodal plane, as you can see right here. So that means it would look much better if you look at this picture right here. And this picture right here, it's just like a watermelon that's been cut in half, right in the middle. So that cut actually can be considered as the nodal plane. Nodal plane, just like the spherical node we discussed before, this is a place where we cannot find any electron. In order for p orbital to appear, n must be 2 and higher. Because L equals to 1, n must have a value that's greater than 1, so n must be 2 or higher. There are 3 orbitals, as we already discussed, 2l plus 1. And here's the 3 orbitals all combined so that we can have a better understanding. All 3 orbitals together. All right, so as for d orbitals, there are going to be 5 of them because L is equal to 2. And how many lobes? 2 powered by 2. It's going to be 4 lobes. So that is why we call the shape of d orbitals as a 4-leaf clover. But a four-leaf clover, so leaf is two-dimensional. I don't think that is appropriate, but we just call it anyway. Okay. Remember, so these orbitals are three-dimensional. Okay, it's not just two dimensions. And one way to understand it, or another way to understand it, is we cut the piece of watermelon twice. One horizontal, and one vertical. So that's why we call it four pieces, four lobes. Speaking of orientation, and most of the d orbitals actually lies in the plane. As a matter of fact, 4 out of 5 lies in the plane. And then even the fifth, we still have a part of this orbital lies in the plane. And the two nodal planes, as we already explained, and again, number for nodal plane actually equals to L itself, like we just explained for the s orbitals. For d to appear, n must be 3 and greater, because L is equal to 2 for d already, and n must be greater than 2, so it has to be 3 and greater. 5 orbitals, because 2 times 2 plus 1 equals to 5, so this is how the 5 orbitals look like. xz, so that means this orbital lies in a plane formed by the y and z, and xz formed in a plane of x and z, and x, so the y is the xy, that means flat plane of x and y. X squared minus y squared, that means not only they are in the plane, and those lobes are actually along the axis. dz squared, however, is a little bit special. Why is it so special? It's way beyond our scope of general chemistry, but I just want you to understand the fifth one's a little bit strange, with a much bigger lobe on the z-axis. Well, let's finally play a little bit of game here. So, what can we predict if we talk about an f orbital? First, f orbital, L equals to 3. How many orbitals? 7. Right? As you count the possible value of m sub L, so we now understand that's going to be 7 orbitals to L plus 1. And how many lobes should we expect for the f sub shell? 8. Because that watermelon is going to be cut 3 times. Okay. In 3 dimensions. 3 cuts leaves the 3 nodal planes. And for L to appear, n must be 4 and greater. So all of this actually can be predicted once we know what the L value is for the f orbital. And here goes one of those 8. Although it's a 7 orbitals. We call the y, f, x, y, and z. As you can see, there are 8 lobes. And there's more. Okay, there are 6 more. And those shapes becomes very much complicated. And for us to concern, I, even with a PhD degree, didn't know too much about the other shapes of f orbitals. Okay, so that is good enough for us to understand that there's going to be 8 lobes. Okay, and n must be equal to 4 greater for us to have the f shells and f orbitals, and there are going to be 7 of those. One thing I'd like you guys to think about, and from this moment on, I'm going to describe electrons as a hyperactive sibling. Okay. So if we have atomic orbital for electrons to stay in this so many different locations, in other words, if we have so many nodal planes to cause so many lobes, in order for electrons to stay in any one of the lobes, there must a cost. There must be a cost. The cost is energy. So we must, in order to have those electrons, hyperactive electrons, restrained in this particular space, electron must be very energetic. And that leaves the door for us to discuss the order in energy of L later on in chapter 7. To summarize here, okay, so we have talked about atomic orbitals, and this is slides where our exam is going to be, right, or our exercise is going to be. So we talk about the atomic orbitals, and the atomic orbitals will come with the 3 quantum numbers to identify. We call the principal quantum numbers, and start from 1 all the way up to infinity if situation requires. 2 functions, okay, so it determines the measured energy and the size of our orbitals. And in order for us to realize just how many orbitals in this principal shell, we understand it has to be n squared orbitals in this principal shell. Angular momentum quantum number is what L is. Start from 0 all the way up to n-1. As the functions, it determines the energy sublevels, and the number of sublevels is equal to n for this principal shell. It also determines the shapes of orbitals, as we already discussed. As you can see, okay, so sphere for S subshell, dumbbell for P subshell, any orbitals in the shell, and that's going to be 4-leaf clover for any orbitals in D subshell. That means 4 lobes. For F, all we can say here is going to be 8 lobes. What kind of shape? There's no solid description for that. Just how many orbitals in that particular subshell of L, that is going to be 2L plus 1. As for the magnetic quantum numbers, M sub L start from 0 all the way up to plus L and minus L in pairs. That means plus 1 and minus 1, plus 2 and minus 2, on and on and on. As its function, it determines the orientation of orbitals. In other words, we can find a particular orbital from a very specific spatial orientation. And each value of M sub L indicates one atomic orbital. That means the total number of the possible value of M sub L equals to the number of orbitals. And that is all for us to understand in this chapter. And thank you for your time. And I'll see you guys in the next chapter, chapter 7. Thank you.